This is Cambria. This is where we're going to go on that 12F field trip, just incidentally. So, if you are in that class, that's great. Just so you know, Central California coast here. If you're still interested but not yet enrolled, let me know, and we can get you enrolled. I think you can still enroll without needing an ad code because the timing of the course is a little different. But let me know if you're trying to add and you cannot, and I'll get you an ad code. Okay, so still opportunity to go there. So we'll be camping on what's called a marine terrace. We'll talk about that later. A terrace, you know that term, right? Like a terrace is, what does that imply when you hear terrace?
There's nothing underneath.
What's that?
There's nothing underneath.
Nothing underneath. Yeah, it's kind of overhanging, right? And it's a flat area. Like a terrace is something you kind of walk out on and you're kind of overlooking things, right? So a marine terrace is just like that, where you've got a cliff along the coast and then you've got this big flat area. That flat area actually represents an old seashore that has been compressed and uplifted. Right? So that's a marine terrace. We'll talk about that later in the course, but that's where we're going to be camping, overlooking this lovely rocky intertidal ecosystem here. So I had mentioned that I was going to show these videos at the beginning of class and trying to get us to make observations of the seashore and then tie into the concepts that we cover. So what are some observations you can make based on what you're seeing or hearing here? You can't smell anything from it, but you see and hear it. Yeah. Remind me your name, sorry.
Karina.
Karina.
I think it's kind of like a kelp forest because you can see all the kelp below the tides.
Yeah, so you see these little brownish things sticking out right here? So that's what the observation is, right? I see these little floaty, look at that right there, right? Sticking up a little bit out of the water. So it's kind of here and there. So that's kind of the raw observation. And you always want to think about like, what's the fact? Karina made an interpretation, and I think it's accurate. I agree with it. It's kelp. Okay, so the interpretation of that is that is kelp. Okay, so that's one thing that you can see along the coast. And then what does that imply when you have kelp?
Otters.
There might be sea otters around here, and in fact there are. Last time we were camping at Cambria, there was this little group of sea otters that were just like tooling around in the kelp, having fun.
That's awesome.
So we'll be able to see those as well. So there may be sea otters. We don't get them in Southern California anymore, used to, but this is Central California, so maybe sea otters. Another thing we're going to talk about in this course is kelp is kind of a unique West Coast sort of thing. So you get a lot of kelp over here, you get a lot of kelp over here. You don't get it on this side. You don't get it on the East Coast. So it's something that you have a lot more of. And the reason being is because on the eastern sides of oceans, like the eastern side of the Pacific, that's where you have a lot of cold water coming from the north. So you have cold water in general coming down from the north. And so and then over here it's coming from the south. So the water is coming from these cold regions. That cold water brings nutrients, which feeds the kelp. So this water is chock full of nutrients, because kelp absolutely needs a lot of nutrients. So we're talking nitrogen, phosphorus, stuff that you use to grow plants, right? The potassium, nitrogen, phosphorus, that kind of thing. So kelp needs a lot of nutrients. So when you see kelp, you can infer that there's a lot of nutrients in this water. And typically the cause of this is because there's relatively cold waters. Any of you ever have visitors that come not from around here, and you take them to the beach and they imagine this happened to me a couple of times. They imagine it's going to be nice and warm running into the water. It's a huge shock, right? It's very, very cold off our coast. And so that's something that hopefully you're familiar with along this eastern side of the Pacific Ocean. We got a lot of cold waters. That's what produces the nutrients, and that's what ultimately leads to kelp. These cormorants flying by, you can see a group of them. Cormorants are these birds that swim hunting fish. Ooh, got a little foraging crow right there on the seashore as well. So you have a lot of exposed critters on the rocks as well. What might that tell you if you have like more exposed critters than usual on the rocks? Yeah.
Maybe it's a certain ecosystem that isn't like inhabited by humans as much. Not many human contact.
So maybe not trampled by humans as much. So when you see more of a diversity, So it could, and you certainly don't see a lot of people around here, right? So it's maybe that's another thing that you see here. So pretty diverse and abundant life on rocks. How come sometimes you go to the beach, the same beach, let's say, and you would see more of the rocks and more of all these critters, and other times you go there and you don't see the rocks at all?
It could be possibly because of the tide.
The tide, exactly. So through the day, we'll talk about tides later in this course. The water level goes up and down. Right. So if you see a lot more of these critters exposed, what can you infer about the tide level?
It's low.
It's low. Yeah. So the water level has receded out towards the ocean. Later on, it's going to cover it up, right? So just by seeing that, you can infer that it's low tide. All right. You can see a lot of wave action over here as well. So as the waves come in, remember they're bringing energy. And as the waves hit these obstructions here, they do two things. They reflect back. You can see some where the waves reflect back, and they also bend a little bit. So that's other sorts of things. Oh, you can see it coming off of there, right? So the wave hits it, and it reflects off of that particular spot. So that's wave reflection. That's something else that you can see. Regular incoming frequency of these waves as well. And if you measure how frequently the waves are coming, that will give you a feel for the overall amount of energy that those waves possess, that set of waves. So those are just a few examples of the kinds of things that you can see from this seat. There's more, but we need to move on a little bit. But this is something that characterizes our planet very nicely. I can leave that up there for now. Actually, while I leave this, why don't I go ahead before I forget and take roll. The ravens too. Ravens have kind of a softer call. It's like a little bit less edge than what the crows have. And crows, well, actually they both forage along the seashore. It's interesting, they've done an ecological study on crows, and they find that the crows, well, you saw the one foraging over there, right, earlier? So the crows will find these, what are called whelks, which are big marine snails, big shells. Thing about, a hard, tough shell is it's a great defense, right? And the snail has this thing called an operculum that's like a shield that closes all of its soft parts in, so it's completely surrounded by a hard shell. So how's a crow going to get the meat inside? So the crows have figured out that they could grab this whelk shell, fly up high, and they've done optimization studies. Yeah, exactly. The crows fly just high enough so that when they drop it, the shell will break open, and then they'll be able to eat it. So it's great, ingenious. So anyway, that's a little of the mystery of crows. That's a cormorant right there. You see, cormorants, I told you that cormorants are the ones that dive down and swim for fish. They're blackbirds, long necks. And so they're very well adapted for going down. There's, you know, when you're in the water, if you're scuba diving, it's with the big tank, it's hard to get down, and so scuba divers will wear a weight belt to help them get down. Birds similarly are kind of like built very lightweight in general, right? So they could get in the air, and they have these feathers that are waterproof. Well, not cormorants. Cormorants have feathers that are not waterproof because they don't dive into the water. They're just floating, and then they swim down. And so they've given up on all of this waterproofness. And so that's why you'll commonly see cormorants. You'll see them out on rocks, and they'll have their wings stretched out like that. And they're just drying out their wings. So because they don't have waterproof feathers. And so that's what they have a series of adaptations that are different from your typical birds. I wanted to mention them because they're very common on the sea, along the seashore. You ever see these birds that are staying about 5-10 feet above the water and they're flap, 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 flap. They're like ducks, you know, all the time. They're not soaring, but they're putting all their might into flapping at all times. That's cormorants. I'll spell it for you. Cormorant. All right. So, what I wanted to talk about today, I want to start off with the origin of the ocean. This is a class about oceanography, so I wanted to talk about how the ocean originated, what we know about how it originated on Earth, and then we'll talk a little bit about the possibility of oceans originating in other places as well. So that's going to be the focus today. So let me get this here. So these slides are available to you. While I'm loading up, are there any questions right now on anything course related? Oh, did you guys fill out your little cards as well? Make sure, you don't have to turn them in right at this moment, but make sure before you leave to turn it in. I forgot to remind you, so if you haven't yet done it, I'll give you a little extension on it because I did forget to remind you. But just before you leave, if you do have that informational card on yourself, turn it in. And then if you haven't yet done it, just get it to me by later today. All right, so there's a famous astronomer. He's kind of the precursor to Neil deGrasse Tyson, called Carl Sagan. And he referred to the Earth as this, the pale blue dot. And he referred to it thusly because he was imagining if there was some extraterrestrial intelligence who had some kind of a telescope, and they happened to be able to somehow shield the light from our sun so that they could get a good image of the Earth, then they would see it's this pale blue dot. And what is largely making the Earth blue?
Yeah.
Yeah, the atmosphere of the ocean in particular, yeah. So having that ocean might excite this extraterrestrial intelligence because they would think that there's a decent chance that there might be life on the planet. Okay? And so it kind of caught up in that statement is this assumption that where you have water on a planet, there's a good chance that you'll have life. Okay. And so that's something that we'll talk about a little bit as we go along, but that's something you can kind of at least begin to think about right now. Now, to understand how the ocean formed on Earth, we first need to understand how the solar system formed. Okay? The solar system, which consists of the sun, all the other planets that are orbiting around the sun, including the Earth, the asteroid belt, right? That's the solar system. The solar system that we're in, which is everything that's gravitationally attracted essentially to the sun, center of gravity of this little system we're in, that solar system exists within a much broader context called the universe. Right, so the universe is all of space and matter that's in it. Now in the text, they go all the way back to the Big Bang, which is the origin of the universe. And so I don't want to dwell too much on the Big Bang because of limitations of time, but just so you know, around 12 to 14 billion years ago, you had the origin of the universe. All energy in the universe was compacted in this very infinitesimally small point, which has began this vigorous expansion that continues to this day. So it looks like the universe is continuing to expand outward. There's not a finite size. It's getting bigger and bigger. But anyway, that was around 12 to 14 billion years ago. Okay, that's what the best evidence from physics tells us about when everything that we know of, that we can see through telescopes and whatnot, our whole universe originated. Now within this universe, around 4.5 billion years ago, something happened to a nebula. So a nebula it looks like a space cloud, basically. It's different than clouds in the atmosphere. Those are water vapor clouds. Although nebulas in space, nebulae, do have water in them. A nebula in general is just this cloud, this collection of gas, ice, and dust. And it's all kind of loosely held together by gravity. Okay, so it's this slowly rotating cloud of gas, ice, and dust. Everything in the universe has some kind of movement left over from the original energy of the expansion. Okay, so it looks static here, but it is slowly rotating, and the reason why it's held together is because of gravity. Gravity is like the glue that's sticking it together. And it's a combination of these things. So gas, we talked about that, various gases. Ice, for example, water ice, so H2O. And other ices as well, potentially. And then dust, little minerals. Tiny minerals. So that's what a nebula is. It's held together. And around 4.5 billion years ago, that's when the nebula where we are began to collapse in on itself. And so this is when the Earth, the Sun, and everything else in the solar system appears to have originated. 4.5 billion years ago. And it all started with a nebula. There's good evidence for this too, based on the planets moving around the sun in the same direction. They're spinning in the same direction. Most of them are more or less have their axis of rotation vertical, except when they're hit by big meteorites, and then they're offset a little bit. So there's a little bit of variation that's caused by big impacts. But those are just some of the kinds of evidences that support this. And we've also been able now with new telescopes like the ALMA telescope in Chile, which can really peer far. We can see solar systems forming today in the same sort of manner that we infer our solar system formed. So just to give you like a little bit of a feel for the evidence, right? Because you should always be thinking it's like this is either a statement, right, or it's a it's either a fact or it's an opinion, right? And some opinions have more evidence in support of them. And so that's why I wanted to explain a little bit of the evidence and support. Abby, did you want to?
Isn't there a planet that's rotating in the opposite direction?
Yeah, because it got completely knocked upside down.
And
Yeah.
Uranus is like completely on its side.
Mm-hmm. Yeah, so there are a few exceptions, but those exceptions could be explained by big impacts. And so let's start with this. So about a little bit before 4.5 billion years ago, you had this nebula, this cloud of gas, dust, and ice that is slowly rotating around, held together by gravity. And so you can see these are your force vectors here. You've got gravity holding it together, and you've got this kind of orbital motion kind of going around like that. Something triggered this nebula to begin to collapse. So from here to here, nebula starts to collapse inward. So as this nebula is collapsing inward, you can see that more of the matter ends up concentrated here. What's this going to end up becoming?
The solar system.
The whole thing will be the solar system, and then this thing right here is going to be the sun. Right now you could call it a proto-sun because it's not quite there, but it's getting there.
It hasn't started nuclear fusion.
That's right, that's right. It hasn't, yeah. So it needs to get to a certain size before it can have enough energy in its core to drive protons together, called nuclear fusion, and release energy, basically for the star to start shining. It's getting there. So this matter is kind of beginning to come together. And so as you get more and more matter over here, the force of gravity, which we'll talk more about when we talk about tides, is proportional to two things. Gravity. The distance between two objects and their masses. So the bigger things are, the stronger the attraction, the gravitational attraction between those objects. That's why we don't fly out into space, even though the Earth is rotating around. The Earth is huge. And so we're gravitationally held by that. So the point is, as this gets more and more matter in the middle, it has a greater ability to draw more stuff in. So there's like a little bit of positive feedback. As it gets bigger, its gravitational pull becomes strengthened. But two things are happening. So more stuff is coming into the middle. This is the next phase right here. You also have this debris moving around, and much like when an ice skater is twirling around, when the ice skater brings their limbs in, their arms in, what happens to them? Their rotation?
They go faster.
They go faster, yeah, exactly. And so that's so stuff is coming in like this, right? And getting closer and closer, but it's also speeding up in this rotation around. And so you end up with these rings of debris. So all of this debris that was in the nebula ends up much more concentrated in the end result, in these really discrete bodies. So most of that matter ends up here, right in the middle, and then you end up with these rings around. And these rings, you have just like this dust that collides with other dust particles and collides with rocks, and so things are just colliding and getting bigger and bigger, bigger pieces. You're building asteroids and things like that. And then ultimately what happens as the planet kind of goes through this, it clears up its orbit of all that debris. It vacuums it all up. And so that's how you're able to get from this phase here, that shows a planet that's rotating around, but all this debris, to over here where you don't have as much debris anymore. So over time, you get this kind of an orderly picture, order out of chaos. All from physical principles, right? So as long as you have energy, you're able to build order out of chaos. And that's what happened here. But you can see it in these early stages, there's a lot of energy, there's a lot of collisions between these objects. And so that's what's going to characterize the early Earth, is big collisions. Okay? So the early Earth, the first geologic eon of the Earth is called the Hadean, for Hades, or hell.
Professor, are we going to have to know Earth's entire geologic timescale?
No, not for this course.
Okay.
You might know a lot of it already.
I'm still a little bit beyond the Cenozoic.
Oh, is that right? Oh, yeah. Cenozoic's not as fun anyway. That's basically now. I like the older stuff a little better. So the thing about this debris, that debris from the nebula, again, most of it ended up in the sun. A lot of it ended up in planets. Some more of it ended up in these the asteroid belt, in comets, and in meteorites. Okay, so all those things were formed in that 4.5 billion year ago period when the Earth was beginning to form from this collapsing nebula. So all the stuff that you see in comets and in meteorites, it's the same stuff that we can also see in nebulae. That you can read the spectra of the nebulae to figure out which elements are in it. That's what astronomers can do. We have some nice astronomy classes here at PCC where you can learn how that's done. And when you do that, you can see there's water in here, there's CO2, there's even some organic molecules that before astronomers found them in space, people thought they only come from living organisms, like sugars, things like that. So organic molecules and all these other things have been found in nebulae. And then these are also therefore seen, organics, in comets and meteorites that formed from that debris and continue to hit the Earth. So a comet, has this big trail. That trail that you see is largely this water kind of sublimating, going from frozen to almost like a gas phase as it's going really, really fast. And so a comet is about half water. There's water in a nebula. There's water and organic molecules that have been found in meteorites. And what I mean by organic molecules, these are organics living organisms. And this was important for astronomers to find, to be able to see that the building blocks of life are ubiquitous. That's the key. Wherever they look, when they look at nebula, they see water, they see the building blocks of life in organic molecules. When they look at comets, that's what they see. When they look at meteorites, you can find organic molecules in these. You can find lipids, like fatty molecules that are all around the outside of each of our cells, sugars, all sorts of things, nucleic acid-like things. So this is important because this is showing us where did our oceans come from? From here. and life originated in the ocean, and it originated on the Earth from these building blocks which were brought to the Earth from the nebula and by these comets and meteorites as they continue to hit the Earth. All right, and that's what got astronomers really excited about the possibility of life elsewhere, right? So we could see that it happened on Earth. That's one data point. We see that these same building blocks are everywhere else. So maybe the same thing happened elsewhere. Now, because of the way that the Earth formed and the other planets in our solar system formed, this first period from 4.5 to 4 GA is giga, and that's billion years ago. Just so you know, if you ever see that G-A, that's giga, Latin, giga anna, like annual years, a billion years. So from about 4.5 to 4 billion years, how much time does that represent in millions of years, would you say?
500 million.
That's it, yeah, 500 million. Does that make sense? 4.5, so 0.5 billion equals 500 million. So this 500 million year time period of Earth's early history was made up of these big bits of debris from the nebula that are still crashing down on the Earth, being attracted by Earth's gravity, brought in, colliding. And this was a relatively short time, and thanks to Jupiter, because Jupiter's so big. It was like a vacuum cleaner, and it vacuumed up a lot of the debris from our solar system.
Isn't there
And
theories that show that Jupiter
cleaned it out.
actually moved inward into the solar system, which helped cause the light-heavy bombardment when it moved back?
Yeah, there's like complications with its movements. Yeah, that's kind of interesting, kind of early history of it. Now, here's Carl Sagan again. Now, this term here, bolide is a general term for some big rocky / icy thing that strikes the Earth. It's a comet or a meteorite. The general term. Because when you look at the craters of the moon, almost all of them are from this time period. The moon formed from a big impact about 4.4 billion years ago. I mentioned that last time. But so all these craters you see, these big craters, they formed on the moon 4.4 and 4 billion years ago. That's one of the reasons why we know that this is the time frame. Because the youngest big craters on the moon are from 4 billion years ago. Telling you there haven't been that many big craters. And whatever's hitting the moon, at whatever rate, you're going to have a similar rate of debris hitting the Earth. And so Carl Sagan said that bolides can take it away. How can they take it away? If there's a big impact.
The dinosaur extinction event when
Yeah, exactly. It could cause an extinction, like all the dinosaurs who are not named birds
the non
died out 65 million years ago. So big impacts can cause mass extinctions where a lot of species die out in a short amount of time. Also, with big impacts, any ocean that might have formed is going to be vaporized. So it could vaporize oceans. And if you have some proto-life forming in an ocean and it's vaporized, that life is toast. So it toasts any life that's forming at this particular stage. So that's how they could take it away. But how come he says they give it?
Some believe that the asteroids and meteorites actually had life that could help kickstart it.
They could have life, but for sure they have
Water.
the water and
Organic.
the organic molecules, yeah. They're bringing them to Earth. So during this time period, they're bringing more water, bringing more organics.
But I thought that like sharks are like as old as dinosaurs, and so.
They are. They're in fact a little bit older.
So how do you vaporize life with them?
Oh, yeah. So I'm talking about this time period here.
Oh. Okay.
Yeah. Sorry. Yeah, I kind of mixed it up, right? Because this is more recent. The mass extinctions is more recent, right? Over here, the vaporized oceans and life. I should make that clear. I'm talking about like the early Earth before there was any sort of complex organism.
So the Precambrian.
Yeah, what's called the Precambrian, if you've heard of that. I never finished this idea. Why are they called bolides? when you see a big crater like that, what caused it? Was it a comet or a meteorite? Who knows? Because sometimes you can't really tell, right? That was a long time ago. Good luck finding it. So anyway, that's why it's used that. So the Earth, you can see here, there's no oceans right there. There's too much energy coming in, too hot. Oceans are not going to be stable. But over time, things can cool down once you reduce the rate of these impacts. Tyrese? Okay. All right. So the sources of Earth's water and ocean, ultimately, originally, from the nebula from which the solar system originated. But it was supplemented by later on you had additional comet impacts. Comets have a lot of water. H2O for water. And meteorites. They can have some water in them as well. Now, a lot of this water, when the Earth first formed from this nebula, a lot of this water ended up kind of internal, inside of the Earth. And so this water is, in order to form an ocean, it's got to get to the surface. And so the way that this water, over time, to the Earth's surface, via volcanoes. Which are these? Essentially, a volcano is like a vent for the Earth, where a lot of heat escapes, for one thing. But then also, after all the hot magma kind of comes out, you then have a lot of gases that are escaping. So these are like the Earth's vents, where the Earth releases heat, but it's also releasing these gases that are internal. And one of the main gases that come out of volcanoes is H2O. So you can imagine early on, during this 4.5 to 4 billion year time period, big impact is going to vaporize the ocean. And with that vaporized ocean, you're going to have to essentially restart the process of ocean forming by this. So this is all how water got onto the planet. And then this is essentially how water is making its way from the body of the planet to the surface. And it's slowly accumulating, and as long as you don't have any big energetic thing that's going to slam into the planet, you're going to be able to ultimately produce a stable ocean. All right? Let me know when I'm erasing if you need me to pause at any point. So they're showing this here. So these volcanoes, they release these gases that form, I've been mentioning the oceans, but you can't mention that without also mentioning the atmosphere, because that's the first thing that's being produced. These are gases, so they're going to be part of this collection of gases gravitationally held by the Earth, called the atmosphere. And then once the water is in the atmosphere, the water is going to naturally, because we'll talk about this later, water has a polarity to it. And so it has a positive and negative side. That's why water molecules like to come together. Condensation happens. And so as you have these little water molecules over here, and the way it looks is kind of like this. The oxygen side of the water molecule is negative and the hydrogen side is positive, and it kind of has this bent structure like this. And so the hydrogen side of one water molecule will be attracted to the negative side, and so that's going to produce condensation, where you go from a gas phase to a liquid, and then it's going to equal rain, and that's going to fall by gravity to build an ocean, ultimately. And really what the ocean is just this big pool of water that's covering all the low points on the Earth's surface, right? It's covering all the lowest points. There's nothing special about this geographic region of the crust that says it has to be ocean, right? Nothing special about it. It just happens to be low. And because it's down so low, this big pool of water on the surface of the Earth has covered it up. So that's why you get ocean in some places and not in others. It's all topography, how high up it is. All right, and so this is where the ocean is coming from. It's these gases released. And then with this atmosphere that you have, that was very nice because this atmosphere warmed up the planet. And allowed water to be stable. It kept, what I should say is kept the Earth's surface at a mild or moderate temperature range. Where water remains in liquid form. What is the term for that process by which atmospheric gases help to warm up the process?
Greenhouse effect?
That's it. So that's the greenhouse effect. All right. Any questions so far? Yeah.
Would Death Valley be one of those low points of Earth where the ocean was vaporized?
Death Valley. So like the dropping of Death Valley, it turns out to be something a little bit more recent. It's something that started around 20 million years ago, as opposed to, so that's something. But if sea level were to rise, enough, and there's a nice connection to it, it could potentially. The Central Valley has been flooded, so the San Joaquin Valley. Death Valley is a little too far in, but it's possible.
Well,
Yeah.
actually, I was about to say, when we had that big rainstorm, I think earlier this year,
Oh yeah,
the valley got flooded.
you got a big lake
and
in
it
Death
turned
Valley.
and it turned all, since it was so hot, the sand was turning into like crystallized water.
Oh yeah, you had
And it was
interesting
becoming
minerals
salt.
forming.
It
Yeah.
became a mini ocean.
Yeah, that's right. Yeah, it is very salty there. Yeah, for sure. And same thing with the Central Valley. There's a big lake there as well.
So if it gets flooded again, do you think like the water would become more permanent, or is it too hot?
I think it's
to
too
where
hot
It would...
for Death Valley. Yeah, for sure. Now, if sea level were to rise enough, the Central Valley could be flooded potentially, but that would take a while.
Well, Professor Wilbur says eventually Death Valley will become
Hey, what?
a new sea because it's being split apart.
Oh, because of the, Yeah, potentially if it continues, it's possible.
Is this around where the Grand Canyon was a ocean?
So yeah, that's over time the continents have moved around and things have been pretty dramatically different. So back when there was an ocean where today is northern Arizona, Grand Canyon, North America was situated like right here on the equator, and it had less landmass than it does today. So because of that, the ocean, that's why you can find oceanic rocks in places like Oklahoma or Kansas or Texas or Arizona. Like, what's an ocean doing there? So that things were pretty different in the past. And it was a kind of a tropical sea based on being centered at the equator. So this is just showing overall the formation of the atmosphere. You can see what the atmosphere is, this thin veneer of gases that are gravitationally bound, but it has enough of an effect on the planet that it's going to warm up the surface and make sure that the Earth's surface stays at this narrow, comfortable range in which liquid water is going to remain. And it looks like the best evidence, the oldest sediments that we know were formed in an ocean are from about 4 billion years ago. So it looks like that first 500 million years of Earth history wasn't a stable ocean. There might have been at some times, but it got vaporized. But certainly by this time, 4 billion years ago, it looks like we've had an ocean, and we've had an ocean ever since, continuously. So from 4 billion years ago until now, we have had an ocean on this planet. And that's what's allowed the continuum of life you had alluded to. All right. So why there are oceans on Earth? It has to be in this right temperature range, right? So I already alluded to the fact that there's this blanket of atmospheric gases that warm. What else kind of determines how hot the planet's surface is?
The sun.
Yeah, do you ever hear of the habitable zone? Or the Goldilocks zone? Some of you maybe, some of you not. So I'll write it down here. The Earth is in, I should say that, Earth is in the, and this one here, Earth has, Earth is in the habitable zone. Goldilocks, because Goldilocks like their soup at a certain temperature. And so this is just the right distance from the star. Our star is called the sun. So it's just the right distance. If it's too close, it's going to be too hot. If it's too far away, it's going to be too cold. That's like Mercury. Too far away. Uranus, Neptune, etc., etc. All those ones that are, those are too cold. And so the Earth is just right in this right range between the two. Hey, so is Mars. But Mars doesn't have an ocean. It used to have an ocean. Doesn't anymore. So what explains the difference? Mars used to have atmospheric gases, it doesn't anymore. The difference between the Earth and Mars is Earth is much larger. So Earth has a suitable size. Earth is suitably large. because the large size does a couple things. Maintains internal heat. And with this internal heat that drives volcanic activity, that then replenishes atmospheric gases. And another thing that that internal heat does is it produces a magnetic field and that magnetic field, as this intense energy from the sun rains down on the earth, it hits our protective magnetic field, making the northern and southern lights. And without this magnetic field, that intense energy from the sun protects from solar wind, intense energy from sun. And this maintains atmospheric gases. It doesn't replenish it, but it maintains the atmospheric gases. It protects them from being stripped away. And so Mars initially had an ocean, but because it's much smaller, it lost its internal heat quicker than the Earth. No more plate tectonics, no more volcanic activity, no more magnetic field. It lost its atmosphere, and then it lost its ocean. Yeah, Abby and
I've heard theories that Venus at one point also had ocean.
That's-
But when the sun first formed, it was not as hot, so they were able to.
That's right, yeah. Venus kind of went the other direction. So with Venus, what you had was atmospheric gases, but not too much. So you were able to, you had a moderately thick, not too thick, so Venus is also in the habitable zone, but Venus ended up with too thick a blanket of gases. And so that's what produced what's called the runaway greenhouse effect, which hopefully isn't our future. And that's why they ended up losing, Venus ended up losing its ocean. Tia?
Wait, so does that mean there was once life on Mars?
Well, that's a question. That's what they're looking for.
So they're looking that there was enough water for enough time for life to kind of kickstart.
Yeah. So the one thing about the Earth that's promising, though, is the oldest fossils that we know about are 3.5 billion years old. There's some that are a little older. Remember that the ocean goes back 4 billion years, and surely there was some life prior to the oldest fossils. There's not a lot of rocks from back then. And so that indicates that on Earth, pretty quickly after oceans formed, life, relatively geologically, life must have originated. And so that gives people hope. Now we have only one data point, so we can't do great statistics on that. We only know about life on one planet, but on that one planet, it seemed to develop quickly. Now, it got stuck in the microbial stage for a very long period of time. About 80% of the history of life on this planet, it was almost entirely microbes, like little things. And so it's not like you had dinosaurs and trilobites and things like that quickly. It took a long time. It took until about 500 million years ago. So it took about 3.3 billion years of evolution to get complicated organisms on Earth. Okay? So, and that's why they're looking for microbes on Mars. You know, they're not necessarily looking for, you know, who knows what you could find, but it seems very likely it's going to be simple, right? Probably. They are looking. All right. And remember, too, it's like that there's always, life could be in a form that is completely unimaginable to us, right? So people are thinking about life like Earth because that's what we know about, but keep in mind, there are other possibilities. So this is the idea of the habitable zone. So you can see Mars is in the habitable zone. Venus is kind of close to it. And there's the Earth right there. And so the Earth is bigger than Mars. So Earth was able to maintain its ocean for longer than what Mars was able to. Too hot, too cold, just right. Now, in about 4.5 billion years from now, the Earth is going to burn through all of its hydrogen, and it's going to go red giant. And when it goes red giant, it's going to expand. And when it expands out, the habitable zone, oh no! So the Earth is now not in the habitable zone anymore. And now maybe you can start to get life develop over here. Potentially. Who knows? But that's a long time in the future, right? So, just to show you that it does vary a little bit. All right. And so there's this connection with water and the origin of life, right? And so you may wonder, it's like, well, what exactly is the cause for that? Well, one thing we know about is even land organisms are mostly water. The thing about the origin of life is it had to start with some chemistry, and it had to start essentially like with molecules absorbing other molecules. And then at some point replicating themselves. That's how it starts. So it's all chemistry. I mean, it's still chemistry today, right? Like your life support system is all happening by chemistry that you're not really directing. It's just happening. And so, in order to like kind of jumpstart this combination of molecules, you need these molecules to be able to come together. Where they can build into something more complex, they can absorb other molecules, things like that. So you need to have some scenario where these organic molecules can move. And they're not going to do that in the air, because they're just going to sit there by gravity. So you need some kind of a fluid medium for those, liquid medium for those organic molecules to move. And in fact, let me write that down first. In water. These, remember, organic molecules, the building blocks of life. And in fact, it's been shown that organic molecules can form from an ocean. An inorganic, no life ocean. Now I'll show you the experiment that indicates that next. And for the fossil record shows that for 3 billion years, of Earth history, all life was in the ocean. There was nothing on land until about 500 million years ago. There's this whole like short history of the universe. I forget what it's called, but they refer to in this early stage of Earth the sun being a deadly laser, and the ocean protects from that deadly laser of UV radiation. So the ocean protects the molecules from destructive UV radiation, ultraviolet radiation, high energy radiation from the sun, that in this early Earth history wasn't blocked at all. So any organic molecule exposed to it would immediately be mutated, destroyed, changed. So the ocean protects you from that, and also from meteorites. You're a little bit insulated when you're covered by the ocean like that. What else pointed I want to make? Oh yeah, I think, yeah, I mentioned that already. Oh yeah, and then you have energy sources underwater. Remember, whenever you're trying to build order from chaos, you need energy. Chaos is loose organic molecules. Order is something that is absorbing molecules and replicating itself. That's order. And in order to get that, you need energy. And so there are energy sources underwater, like these hydrothermal vents, they're called. And so this is where the hydrothermal vents are all, remember I mentioned that stitching over there, that's where the plates are pulling apart. That's where magma's coming close to the surface, that's where energy's coming out. So a lot of origin of life researchers, people who are studying like how it might have originated, think that these hydrothermal vents might hold the key. Because of the fact that you've got this energy, you've got organic molecules down there as well. They're very well protected down that deep. So this is why I think there's been a bias in the search for extraterrestrial life towards looking for planets that might have an ocean for these reasons, yeah? Yeah.
Didn't they find a planet that had like the ocean, like Planet X or something?
Yeah, so there's certainly been a number of planets that are considered Earth-like in terms of they seem to be about the right distance from the star, and so and there are they did their liquid water has been detected in at least one of them. That's right, and so with the James Webb Telescope. You know, the hope is that we'll get more information about these other planets. Yeah, and this kind of a point I don't know that I've emphasized well, but the reason why, if you talk to astronomers, most astronomers think that it's very likely that there's life outside of the Earth. And the reason being is because they're aware that there are billions of stars in the universe, and these billions of stars have billions of planets in total, and if even a tiny fraction of billions and billions has life in it, that's still indicating that there's probably a decent amount of life elsewhere in the universe. Now the question is, what stage is it at? And where's it at? You know, is it just microbial stage? You know, has there been intelligence somewhere else? The universe is so large that there could just be these two immense spaces between intelligent civilizations for that to as an explanation for why the contact hasn't been made yet. But that's why astronomers are optimistic about it. So the kind of the 2 points, right? Number one, how many planets there are, and we've been able to observe at least like 5,600 planets. It's hard to see planets because you're looking far away and you see a star, and that star is giving all this light, and relative to it, so far away is this tiny little planet. It's very hard to see. So initially, the way that astronomers could tell if a star had a planet, they would measure the luminosity coming, the brightness coming from the star. So they would see it's bright and it gets a little dimmer. And then it's bright and then it gets a little dimmer. And it's like a metronome, right? It was like a regular sort of thing. And so they thought, oh, there must be a planet that happens to be passing between us, and that's just cutting down the light a little bit on that star. So the point is, there's a lot of planets out there, but it's very hard for us to see them. Most of them are very far away. We're getting some information from them. We're now aware that there's about 100 or so, maybe a little less than that, planets that appear to be in the habitable zone and potentially could have water. Okay. So more and more are being discovered all the time. And with James Webb, that's just going to increase. Okay. So that's why astronomers are kind of optimistic about this. All right. So I had it in class assignment, but I think what I'll do is I'll finish this, and then the assignment for today will be just the that card later on, just a FYI to you all. All right, so remember I mentioned that organic molecules have been shown to form from an early ocean? So the way that this was shown is that these folks, Stanley Miller and Harold Urey, beginning in the 1950s, what they did is they created this device where they simulated the Earth's atmosphere by pumping in gases. These are the gases that come out of volcanoes. So that's the raw atmosphere of the Earth. And so they added an energy source to these gases, a little condensation, a cooling system here to change the water vapor into liquid water. And then they were able to analyze what was accumulating down here in the ocean. So, and what they found is the bonds of these molecules, like methane CH4, H2O, H2, and H4. So the bonds between the atoms in these molecules were being broken by this energy source, and they were reforming. And they reformed in the ocean as organic molecules, including, ultimately, they found amino acids, which are the building blocks of proteins. They didn't find proteins, they just found the amino acids, but amino acids, when linked up, produce proteins. They found lipids, nucleic acids like DNA, similar to DNA and RNA. Sugars. I say there's another organic one. That's crazy, right? So basically, just by breaking the bonds of these very simple molecules and letting them come together, self-organize, order from chaos. Now you've got these organic molecules that are the building blocks of living organisms. So this is showing, the point of this is that in the early Earth ocean, their conclusion is that you would get organic molecules continuing to form. And in that scenario, and that's important because they're the building blocks of life. And that's step one of the origin of life. All right. Does that make sense? Yeah. Groundbreaking experiment. That's so simple too, right? That's the beauty of it. It's a simple experiment, and it's so effective. All right. So I'll talk about these little dudes later. This is what the oldest fossils look like. I'll just show you now. You can see the name. I'll have to come back to these little dudes later. But these are little structures made by microbes, cyanobacteria. These bacteria like spirulina, if you've ever added that to your smoothie. Spirulina is a type of blue-green algae, it's called, a cyanobacteria. And these cyanobacteria make these structures that look like this, and that's what the oldest fossils that we know about are. And if you take the rocks in which you find them and you cut them really thin, so you can and you look at them, you can see these little cells of the little photosynthetic cyanobacteria. So that's what the oldest known life is. And this is a good thing to know. So this is a photosynthetic bacterium. And photosynthesis is important for us because us as animals, eaters of things, because what does photosynthesis give us? There's two things it gives us.
Nutrients.
Food, yeah, so that's one.
Oxygen and sugar.
Yeah, that's right. And oxygen to breathe, to process that food. So ultimately, it's photosynthesizers, like these cyanobacteria, and then later on algae and plants. Those things make the food as well as the oxygen that we need to burn that food. And so you notice the early gases didn't include oxygen. Oxygen came on this planet entirely from photosynthesis, almost entirely from photosynthesis.
Didn't oxygen truly form once the Red Band formation stopped because all the iron was sucking the oxygen out?
Yeah, there was a lot of iron in the Earth's oceans that was sucking a lot of the early Earth's oxygen, taking it out of the Earth. But these guys kept photosynthesizing, and they overcame that, and eventually oxygen levels were able to fill it up. Abby's a little bit of a shill. She's taking more geology classes here. All right. And so in terms of water and life outside Earth, there are some possibilities. We know comets and meteorites, right? We've seen them in comets and meteorites and nebulae. Now, what about in our solar system? Pluto has been found recently, not that long ago. Even Pluto has some ice. By the way, the reason Pluto is not considered a planet, some people really got hung up on that. It hasn't cleared out its orbital path of all of its debris. And that's one of the definitions of a planet that astronomers like. Yeah.
So does that mean it's like still getting bigger?
Yeah. Yeah, it should be over time. Remind me your name?
Sam?
Sam. Slowly though.
It's a planet in my heart.
Yeah, it's a planet. Yeah, I know. Yeah. A lot of people still like Pluto. And Mars has an ice cap. And so that ice cap, remember, used to be molten. And then there's definitely lots of indications on the Martian surface of water flowing and having flowed not that long ago. There's little river channels. Maybe it's a sandworm.
Wait, is that like zoomed out or zoomed?
Yeah, this is zoomed out. Yeah. So this would be like
Oh, so that's
not like Grand
really
Canyon,
big.
but it would be a pretty big. Yeah.
Oh wow.
Yeah. Yeah, that's a problem. There's no scale. If you notice, like geologists always put a hammer or something for scale, but if you're looking at the surface of a planet, there's usually Nothing you can use, unfortunately. All looks the same. And then they've also found a lot of ice that's just under the surface that periodically melts. So this is just showing as the ice melts, you get the water flowing down. So there's definitely signs of water, even currently on Mars, but it's mostly in ice form. In the past, it was liquid, and it was at least some form of ocean. The Mars Perseverance rover is still persevering, still up there, going around. Yeah, I think it's been about 3 years now, something like that it's been. So pretty successful. One of the things it's looking for is fossils on Mars. So, but it doesn't look like, there's certainly no complicated life on Mars, right? Nothing that obvious so far that we've seen. But there could be microbial life and there could be fossil life.
If you put water on the planet, would it stay?
You would want to, yeah, it's try to terraform it. You would want to try to build up the atmosphere. The problem with it would be it's too cold on the surface. So you would need to do something to warm that surface. So you could do if you have like a greenhouse or something like that, like a big greenhouse on Mars. Or otherwise you'd have to figure out some way to keep replenishing the atmosphere. Oh yeah.
I don't know if this is true, but like I don't know if the source is true, but someone said that like there might be an underwater like ocean inside of Mars. I don't know if that's like,
Oh, yeah. Speaking of underwater oceans, there are some places where there for sure seem to be underwater oceans. So there's certainly like water like below the surface, like here, definitely. But if you go a little elsewhere in our solar, that was a great segue. One of the moons of Jupiter, Europa, has an icy surface. So this is all water ice, and it's broken up in these cracks. And based on models, the gravitational force of Jupiter on Europa would produce enough heat internally where it's thought that you would be able, down here, this is where the heat's coming from. It's hot here, right? It's cold over here. And then this is where that ice is meeting this hot interior. And the fact that there's liquid under here would explain why you're getting the cracks and the movement on the surface. And so it's almost definite that there's a liquid water ocean on Europa. So Europa, one of the moons of Jupiter, there's real good evidence that there's liquid water under there. And folks at Caltech have been talking, you need to like land some kind of a drill, right? And like drill through kilometers of ice in order to get to it, and then send down some ROV to try and see what kind of things are down there. So people are thinking about it, just the FYI. But until we can get through this crusty ice on the surface, no one's going to know. Okay. But there's definitely a possibility there. And the reason being is that internal heat is going to produce the same thing that I talked about over here, those vents all along that. And so you're going to have vents under here, and that heat that's being produced is going to produce energy source. You got water, you're going to have organic molecules for sure forming. So you could have life under there as well. Similar thing, it's been found in Enceladus, one of the moons of Saturn. It has this water ice surface like this, and not only that, it has geysers that shoot out. And with the geysers, whenever you have geysers, like water shooting out, that tells you there's some heat. There's some heat underneath. And so similar sort of thing. Saturn's a big planet. It's going to produce a lot of heat on this core of this moon. And so that's going to melt the ice down here. And so you've got this big ocean, again, capped by that ice under there. So it could be something like what you see in these hydrothermal vents on Earth, because you have whole communities of organisms that are fed the chemicals essentially that are coming out of these hydrothermal vents. So we've got communities of organisms that rely completely on the energy coming out, on deep underwater there. And so the idea is maybe something similar in Europa or Enceladus, something where it's coming up like that. So keep in mind though that these examples here, and this is promising, right? These examples are just within our solar system. One little tiny infinitesimal small fraction of the entire breadth of the universe. And that's why astronomers, if there's so much promise just in our solar system, what about elsewhere? That's why astronomers think oceans are likely elsewhere, number one. More oceans than what we just got, and then number two, that at least some type of life. Does that make sense? All right, any questions or last comments? This is a great job, everybody. So yeah, like I said, so the assignment for today, remember every Thursday there's going to be assignment. This time we'll just have it be this, that informational card. So make sure before you leave, you turn in that informational card about yourself. Again, like I said, I meant to remind you and I forgot to do that. And so if you haven't yet done it, just do it by the end of the day today and put it underneath my office E210G. But if you have it, I will take it.
Where do we turn it?